Hi, and welcome to the last lecture on multi-agent learning. This lecture is very practical oriented because we discuss how other researchers compare multi-agent learning algorithms empirically. So the motivation for this presentation is to consider the methodology of other researchers and to see how ML research matured from basically very ad hoc comparisons to rather systematical and methodological comparisons with a strong methodology. So at the outset, when multi-agent learning research just existed, algorithms were proposed just by inventing a nifty ML algorithm and then compare this nifty algorithm with a handful of other existing ML algorithms on a number of well-known games, and then to boost with the performance of your own or the newly proposed ML algorithm. And that's of course quite an ad hoc way of doing research. Later, multi-agent learning algorithms were compared more systematically by pitting games against each other through elimination, knockout tournaments, through evolutionary approaches like with the replicator dynamic. And today we will look into the methodology of what that is the approach and the methods, that is the tools and the software that the various authors use to compare multi-agent learning algorithms. And today the algorithms themselves and the choice of the algorithms and the outcomes of the comparisons are of secondary interest. So we're more interested in the methodology rather than the results. The work discussed is by Robert Axelrod, who organized one of the first tournaments among game learning algorithms. And those algorithms were tailored to the iterated prisoner dilemma. Then we discuss work of Sawatzky and Kevin Layton Brown and Asher Lipson, who did the coding, most of the coding, but together with Eric Sawatzky. This is kind of straightforward but very thorough work. Then we discuss work of Busey, and we discuss work of Areo, sorry for the pronunciation, on evolutionary dynamic. So let's take a step back and let's reconsider the ground table. So all comparisons among ML algorithms start with the ground table, with a ground table, which is an overview of head-to-head scores. So entries are performance measures for the protagonist, for the row, which is almost always the average payoff. But you have also other measures like no regret, and then the entry in one row is the regret of playing algorithm 1 against algorithm 2. And this is the regret for algorithm 1. Now often each entry is computed multiple times to even out randomness if the algorithm is stochastic. Sometimes algorithms have a settling in phase, or also known as a burn-in phase, in which payoffs are not recorded. So you wait until algorithm's performance stabilizes and then you start recording the payoffs. But then the problem is, of course, when do you start to record the payoffs? And with one master student, which I was discussing this was a recurring issue of discussion, that the number of when to start recording is rather arbitrary and difficult to determine. Next slide. So first we discuss work of Axelrod, which is quite famous but rather dated, but still important. So who is Axelrod? That's the man on the left. Was an important contributor to Of course, he's the man on the left. So important contributor to science and to economic theory, for which he received the National Medal of Science in 2014 from the hands of Barack Obama. So in Axelrod's tournament there is one game to test the prisoner dilemma, and in the first tournament there were 14 contestants and one random algorithm, which makes 15 algorithms. And among the contestants there were tit-for-tat, Shubik, algorithms named Nidegger, with all kinds of curious names, and of course random. Most of the response rules or learning algorithms were not really learning algorithms, but mostly reactive algorithms, and we could hardly speak of learning. And all pairs played 200 games. 200 rounds in one game, and this was repeated 5 times. And the winner from this first tournament was tit for tat. And then I think a year of 10 passed, and then quite some time passed, and then a new tournament was organized, and people could learn from the first tournament. So they were able to, they have no knowledge that tit for tat was outperformed all the other algorithms, and they had the opportunity to write smarter and niftier algorithms. So the second tournament accommodated 64 contestants, and all contestants were informed about the result of the first tournament, like I explained. And again, the winner was tit for tat, which was quite an astonishing result, because tit for tat is a very simple algorithm, and still it outperformed all the other 63 contestants. Still, research on iterated prisoner dilemma is ongoing, as even of 2012 there is ongoing research in which I participated as well, together with a master student, on zero determinant strategies, which is quite a new development in games on tournaments on the repeated prisoner dilemma. And those zero determinant strategies outperform older strategies. So if you search my name on Google Scholar on zero determinant strategy, you find a publication there together with a master student. He did most of the work, by the way, which is really true. Next slide. So we first discussed the work of Sawatzky and associates. Sawatzky studied fictitious play, determinate, which is a form of Boolean, awesome, which is a stage learning algorithm, quite complicated. Meta is also a stage learning algorithm, so it is constituted of simpler learning algorithms like Boolean and fictitious play. And for example, first you start with Boolean, and if you discover that your opponent is not responding to Boolean, then you switch gears, so to speak, and you start, for example, a phase in which you play fictitious play. Wolf Ego, you're familiar with. Min-max Q we didn't discuss. Well, the name of the algorithms are not that important. Motivation for this set of 11 algorithms, other than that were state-of-the-art algorithms, wasn't given. And the games on which these algorithms were tested was a suite of 13 interesting families of games, which the first family of games were games with random payoffs, in which the payoffs were chosen that they were normal covariant. Don't ask me. Don't ask me now what that means. Think of it as a suite of random games, and then the other games, just for naming them for the sake of completeness, were games of a specific type. In total, there were 13 families of games, and those 13 families of games comprised a game suite. And those all games, curly D, comprised 600 games, and subdivided by 100 games for each size, so 2x2 games, 4x4 games, all among 2 players, you see. So it's all games for 2 players. 8x8 games, 10x10 games. And then 100 games, so these comprise 500 games. And the other 100 games were taken from Rappaport's catalog of 2x2 games. Rappaport's catalog of 2x2 games is a collection of Prisoner Dilemma, Battle of the Sexes, Stag Hunt, and other typical 2x2 games, and avoid replication of 2x2 games. So it's a quite representative collection of 2x2 games. And then the ground table was formed by letting each algorithm play all pairs, play each other algorithms on those 600 games for 10,000 rounds. And the evaluation of the performance was through statistics and looking at squared heat plots, which we will do now. Which we will do in a moment. And the conclusion was that Q-learning, which is a very simple learning algorithm, and we have discussed it in the lecture on reinforcement learning, is the overall winner. So this is quite a, daunting result, because you didn't see that coming, because these algorithms were quite sophisticated. Next slide. So the most coarse way, the most global way in which you can compare the algorithms is on their mean performance, the mean reward. And if you compare those algorithms on the mean reward against all other algorithms, well, these are this is the distribution of Q, of the reward, with here the mean, and the points here are probably, 2 times or 1 times, I don't know, the standard deviation. So some feathers, this is a feather plot I suppose, are more stretched than others, which means that the variation is higher. Of course, a random performs worse. Then another measure of performance is regret. And among all algorithms, the mean regret of Q-learning was the smallest, and of course random had the highest mean regret. Performance was also compared through heat plots. So one of those heat plots is on the x-axis, all game suites. So these are all games. The algorithm is tested on all games in suite 1, which is the suite of all random games, and this is the suite of all Cournot oligopoly games, and so on. So just 13 suites of games, and you see, for example, that random performs very badly on the subset of games or the type of games, game types D6, and you see that Q-learning performs very well on nearly all games, game types, except on game type 6. So game type 6 is apparently is a quite a difficult game type to learn on. Obviously, learning algorithms were compared against each other, and the color represents the performance of the row player. So you see that Q performs well against every other algorithm. Q performs well against every other algorithm, especially against itself, you see. And random performs quite badly against every other algorithm, especially against Q-learning. Next slide. So the performance was also compared with statistics, and one way to compare games with statistics is through the paired student t-test, to the paired t-test. So what you do is you have two learning algorithms, A1 and A2, and you can compare them if you can compare their performance in equal conditions. So the first equal conditions for both algorithms is when they play against A1 on G1. And if A1 plays against itself on G1, it has an average payoff of 2.1. And if A2 plays against E1 against G sub 1, so in entirely identical conditions, then perhaps it has a payoff of 2.7. These are just random numbers I've filled in to suggest a concrete example, but these are in fact just random numbers. So these are random, so each column here is here A1 G1 is a similar condition, A1 G2 is a similar condition, A1 game 3, A2 game 1, A2. So we have a very long array of which we have only written down only the first 9 entries in which we have similar conditions. And of course you can compare this number, the first two first numbers, and the second pair. You can compare the second pair, and you compare them for a significant difference. So you compute the average difference, which is a stochastic variable. So the difference between this one is 0.6, and between this value and this value is 0.4, and you take the average of all differences and the average standard deviation of differences of all those n pairs, of which we see 9 here. Now if those two series here, so the first series and the second series, are generated by the same algorithms, or by the same random process, the following test statistic, so the following quantity, so this is the average difference divided by the average standard deviation divided by the square root on the number of rounds. So this value is basically normalized, and then this normalized value is called a test statistic, because we know if both rows are generated by the same process, it should follow the student's t distribution with mean O and n-1 degrees of freedom. We know that if we suppose that they are generated by the same random process. Now if the value of t happens to be far away from 0, it's too eccentric, so far away, too far away from 0 is not near 0, then it's quite unlikely that the two sequences indeed are generated by the same random process, and we have to reject this hypothesis. And we also say that well, if this the probability that this value of t is generated by the same random process is very small, has a low p-value, the probability that this value of t is generated by those two has a low p-value, then we say we have to reject that, and we can more or less safely assume that the two algorithms perform differently. Even if you do a one-sided t-test, one-sided paired t-test, then you can, for example, say A2 performs better than A1. And you can do that for all couples. There's something to be said about doing this for all couples, because the problem when you compare multiple pairs of algorithms, then you have to correct for unjustly discovering significance. Oh well, it's difficult to explain. So when you do multiple comparisons, then it's more likely that you discover significant results. So you have to correct. Here you have to correct for this. So it's not an entirely trivial matter. So let's move to the next slide. So when you do a paired t-test on the performances of the different algorithms, then this is a screen dump of a student's project some years ago, and this is random UCB, and you see that satisficing play has quite a high variance in its performance against other algorithms. Markov is an algorithm that remembers what it has played previously and plays that action that has proven success with a particular history in previous rounds, but takes a lot of memory, Markov. However, the problem is that you can't assume. Well, let's go back. You can't assume that this data here is distributed normally. In the graph I just showed you a few seconds ago, it is tested and it was distributed almost normally, but you can't assume that. You must test for normality, and in statistics there exist several tests for normality, and you have to do that in order to indeed be able to perform a paired t-test. But if you can't do that, you can resort to non-parametric test, and one such example used by Sawatzky et al. Is the Kolmogorov-Smirnov test. Again, you have two distributions and you have two hypotheses. You assume that they are generated by the same process, yes, and the alternative hypothesis is that they are not generated by the same random process. So this is a performance of the first algorithm here as a cumulative distribution function. So the values of performance are just added. And here as well for the second algorithm. And the Kolmogorov's non-parametric test looks at the largest difference between those two distributions. For example, that's here. Let's suppose it's here, the largest difference. Now the p-value is the probability of seeing this largest difference while assuming that both cumulative distribution functions, both empirical cumulative distribution functions, are generated by the same process, are generated by the same theoretical distribution. And if those pair of cumulative distribution function has a low p-value, so then it's very unlikely that those two distributions are generated by the same process, and you may safely conclude that the two algorithms, the two learning algorithms, perform differently. This is further explained in the paper of Sawatzky, but the method itself is purely statistical and you can find in any statistic textbook. So Sawatzky et al. Investigated relation between game size and rewards, and they found no relation, and they performed a number of other side quests, so to speak. Correlation, they investigated correlation between regret and average reward, and correlation between distance to nearest Nash and average reward, because simply measuring on average reward alone may not yield information, but measuring the distance to your average reward to the nearest Nash and comparing thus the difference between the different algorithms may yield suddenly interesting information. Which algorithms so-called probabilistically dominate which other algorithms, and it is a bit reminiscent of the Kolmogorov-Smirnov test. It's another concept, and it's further explained in the paper of Sawatzky. And the outcome was again that Q-learning is the only algorithm that is not probabilistically dominated by other algorithms. And they compared algorithms by means of taking the difference between average reward and the max-min value, which is safety value. And again, Q-learning attained an enforceable payoff more frequently than any other algorithm. So the bottom line of all those 2 points is that whichever performance measure you worked with, Q-learning turned out to be the best performing algorithms for all those performing measures, at least according to Sawatzky's research. Next slide, where we talk the work of Busey and associates. So Busey discussed the learning algorithms minimax, fictitious play, Q-learning, satisficing play, M cubed, which is quite a complicated learning algorithm, therefore we didn't discuss it, and some other learning algorithms. It was tested on random 2-player games of 3x3, which payoffs in Z, with the integer payoffs in this interval, if I understand correctly, and otherwise in the continuous interval. Each pair of algorithms plays 3 million rounds on a random game, and it was restarted. Each head-to-head encounter was restarted 100 times. And curiously enough, Busey et al. Ended with a different ranking than Sawatzky et al. They found that UCB performed best, upper confidence bound, as you recalled it, and they plotted the performance of the algorithms with respect to performance in a graph, and the researchers were familiar with the work of Orio and Sawatzky. And curiously enough, contrary to the work of Orio and Sawatzky, the ranking of the algorithms still fluctuated after 3 million rounds. So that's quite astonishing. So that means that one has to test quite beyond some far horizon to arrive at the final ranking of learning algorithms. So one variation of comparing algorithms of Busey was to eliminate by rank. So rank the algorithms by performance, eliminate the worst performing algorithm, and subtract all payoffs earned against that worst performing algorithms that the survivors have earned, because the worst performing algorithms was worthless and non-informative anyway. So, and then repeat. and they finally end up with m cubed as the best performing algorithm. The other type of knockout tournament was to eliminate by lag in performance, and if the difference between the cumulative returns of the two worst performers after repeatedly organizing a tournament is larger than some threshold, which is empirically determined, I suppose, then the worst performing algorithm is removed. And if that didn't happen, then the worst performing algorithm was removed. Is the global ranking didn't change after so many tournaments since the last elimination, then the worst performing algorithm was also removed. And the final ranking was, well, at least the top three was similar to the top three with the other knockout method. And here you see the ranking evolution according to the number of steps played by games in log scale. You see on the x-axis the log scale. And the keys are ordered to the final ranking, so U to B performed best here, eventually. And then m cubed and so on. Next slide. So this is ranking based on eliminations by lagging. And again, the keys are ordered by final performance. By final ranking, sorry. So variations in this refers to select subclasses of games to, for example, only measure performance on cooperative games, and then X3 was the winner. To compare only on competitive games, and then X3 was again the winner. To compare only on specific matrix games, like the penalty game or the climbing game. You can Google on this if you want climbing game, specific type of game, coordination games. On a different number of actions, and the global conclusion was that m cubed performed best. The performance was measured not in terms of plane averages, but on rolling averages or geometric means. Another interesting direction that was indicated by Busey and al. Was that exploring why X3 performs so good in cooperative and competitive games, but not in global general sum games, and to investigate this fact. The last work we discussed is of IREO and the Associates of 2007. Here the contestants were Max Min, Nash, generalized tit for tat, best response, fictitious play, best response, fictitious play. You play best response if you suppose that the other is a fictitious player. Bully, Sabi. I did a lot of work because Sabi was the best performer here. I searched very hard about specifications of Sabi, what was just unretrievable, which is of course very worse scientific practice, because scientific results should be reproducible. The motivation for choosing this algorithm just plainly was we choose well-known algorithms, which I find to be quite a rather loose motivation. The algorithms were tested on 2x2 normal form games, taken from Brahms' taxonomy, with the argument, so it's comparable to Rappaport's taxonomy of 2x2 normal form games, kind of periodic system of 2x2 games, like in chemistry, the periodic system in chemistry. The ground table was computed by letting each algorithm pair play a random game for 1000 rounds, significantly less rounds than, for example, Busey, which took, as we recall, 3 million rounds, and to restart 20 times. And the methodology to compare it was to perform some form of evolutionary dynamics. So to start with a population of algorithms, and to start with an initial proportion that is reciprocal to the performance in previous experiments. So good performance, we're getting a small share, and worse performance, we're getting a large share at the outset. And then they applied, for example, fitness proportionate selection through the probability to select is 1 plus delta divided by delta max divided by 2. So these numbers had to add up by 2, 1. Otherwise those aren't probabilities. And delta is some normalized performance measure. And the final ranking here was best response to fictitious play. So you see a kind of dynamics here that is reminiscent of the replicated dynamic, in which proportions fluctuate but finally converge to a fixed proportion. And not all algorithms participate here. And here finally best response fictitious play comes out best. Other algorithms die out except fictitious play and SABI, of which we don't know the definition. So here are some others. So the authors experimented with different mixes of algorithms. And in this mix, fictitious play comes out best. So these were the contenders here. And in another mix, so it depends on the mix which algorithm comes out best. Best response fictitious play comes out best. So here it was with the tournament description selection as described in a few moments ago, and this is with another evolutionary selection method. So we repeat the implication of this presentation on the replicated dynamic. So again, the green nodes concern the replicated dynamic, which is can be seen as a dynamical system, so a point that moves in space and is guided by a differential equation. And we see that the Nash equilibrium, every Nash equilibrium is a fixed point of the replicated dynamic, but conversely this need not be true, and there are counterexamples. And every stable point, or every, which is the same to say every Lyapunov stable point, or stable point for short, is a Nash equilibrium. If you have difficulties with recalling this picture, then look up my presentation on the replicated dynamic. And also, if you start in the interior, the star denotes the interior. If you start in the interior of the strategy space, so every strategy receives a non-zero proportion, and the dynamic converges in the replicated dynamic, then you know for sure this is a Nash equilibrium. So if you work, I already explained it in the presentation on the replicated dynamic, if you work with the replicated dynamic, you should give all contenders a positive probability, because if you have convergence, there's not always convergence, but mostly there is, you are certain that you have arrived at a Nash equilibrium. And of course it's very natural to give every contender a positive probability, because you want to give every contender the benefit of the doubt, to give a fair share to take part in the competition. So this is a very reasonable assumption. Well, this one here. So if you have a limit point in the replicated dynamic, and that replicated dynamic started in the interior, then you arrive at a Nash equilibrium. If all this doesn't make sense to you, please go back on my presentation on the replicated dynamic. Okay, we arrive at one of the last slides. So the replicated dynamic and the Nash equilibrium have some relation. So let's reconsider the ground table, and you can look at the ground table as a game in normal form, and you can compute a Nash equilibrium of that game in normal form. And I just explained that every fully mixed limit point of the replicated dynamic is a Nash equilibrium, and conversely, every Nash equilibrium is a fixed point of the replicated dynamic. So Nash equilibria and limit points of the replicated dynamic are closely intertwined. They're not equivalent, but almost equivalent. So 1 and 2 surely help to isolate interesting combinations of response profiles. For example, if A2 against A12 is a Nash equilibrium, so pure Nash equilibrium, then we can say that if we have to choose an algorithm against a player who avails himself of this algorithm A12, then we know for sure we have to choose the second algorithm. But this also holds for mixed equilibria. So if you have a mixed equilibrium of A2 and A12 against A1 and A2, suppose it is a mixed equilibrium, A1 and A2 in a certain proportion against A2 and A12, then this is a status quo, an equilibrium among those algorithm combinations. So so what I want to convey here, that it is interesting to interpret Nash equilibria on the grand table as outcomes of a comparison between those algorithms. And those outcomes may not be as having mixed equilibria and many mixed equilibria, because large games in normal form have many Nash equilibria, and many mixed equilibria for that matter. So this is not an unambiguous outcome of a comparison among algorithms, but it may be the best outcome you can have, because comparing algorithms against each other, then you may not expect an unambiguous outcome, like for example A1 is the best or A12 is the best. But the best outcome you have is a set of Nash equilibria, perhaps. So let me close this presentation by generally evaluating the different methodologies. So first, the selection of learning algorithms to test on. My take on this is that all approaches demonstrate quite some arbitrariness and lack of method in choosing the learning algorithms to test on. Then the second point of criticism is that the algorithms are all different. They assume different knowledge. Some algorithms assume nothing, like reinforcement and satisfying play, and other algorithms assume knowledge of the payoffs of the opponent. And without going into the terminology here, you have to have followed the lecture on coupled and uncoupled play. Well, the point here is that algorithms use different knowledge, and so they can't be compared on an equal footage. So this gives an unequal playing field. So it's quite surprising that Q-learning performs very well, even if it doesn't use that much information as, for example, Bully, which uses the payoffs of the opponent, which needs information on the payoffs of the opponent. And some algorithms are very simple, and other algorithms are computationally expensive and need, for example, to compute all Nash equilibria, or the nearest Nash equilibrium, which amounts to the same. So the computational complexity of algorithms is also not taken into account. So the point is, algorithms are born differently, and still they are compared on the same field, which is not fair. So we should have different leagues: coupled algorithms, uncoupled algorithms, and completely uncoupled algorithms. The terminology here I didn't discuss, but it is discussed in another lecture. Basically means coupled algorithms use different type of assumptions than uncoupled algorithms. And then the third problem is that many algorithms use parameters, and for every parameter the dimension of the search space increases. So this gives uncountably many sub-algorithms to test on. Then the selection of games. The approaches demonstrate a poor method and are rather arbitrary. So their justification of choices is weak and subjective. To test on 2x2 games, but why not test on 2x2 games for more than 2 players? So 3 players where each player has 2 actions. And why not test on games not only in normal form but on extensive form? And then if that's too much work, then say so in your paper. Do not be silent about it. Then there's a problem that the selection of sub-contestants, so to run tournaments in which some contestants are left out, yields completely different rankings. So how do you choose your algorithms to play against each other? For example, suppose algorithm A performs best in the presence of algorithms B and C, thanks to C. We already discussed this in one of the first presentations on the programming assignment. So A is a particular example of this is old effect performs best in the presence of tit for tat and all cooperate. But if all cooperate disappears from the stage, then suddenly old effect performs very badly against tit for tat. So it makes a difference how you pool the different algorithms against each other. And the question is how to deal systematically with that. So we saw that Busey had some approach by eliminating the worst performing algorithm and then subtracting the winnings against the worst performing algorithms from the surviving algorithms, but just one method. Then the problem of dealing with evolutionary selection, how to select algorithms: fitness proportional, by tournament selection, by reward-based selection, by other selection methods, by replicated dynamic. than the problem of organizing knockout tournament, how you decide when and where to drop the worst performer. We saw that Busey made some choices here, but those choices aren't very well explained. And of course the order of elimination puts a bias on the ranking. The order of elimination may be wrong, and then it influences the ranking. The probability that it is wrong is small, but it is still present. So these are some of the problems of organizing tournaments among multi-agent learning algorithms. So coming this far, I think you know enough now to continue and complete your programming assignment, and to draw up a sensible discussion in which you compare your own work with the work of Irio, Sawatzky and Busey. So since this was the last online lecture, I wish you all the best and good luck with the completion of your programming exercise. Thank you for listening. Thank you for bearing with me all the time. Good luck, and maybe we will see you again on the other side. Bye bye.